So now we're going to talk a bit about the alternating series test for convergence. And basically, if we have an alternating series, so if we know it's alternating, it has one of these negative ones raised to some n power, and that power could be n, it could be n minus 1, it could be n plus 1. It just depends on your index, okay? So as long as we have an alternating series, then we can examine that nth term. And so we're using u sub n here for the term in our alternating series as opposed to a sub n. It's just a difference of variables. So when we look at adding those up, we would have plus, minus, right? So we have an alternating series, and this will converge if we can show the following three things. We need to show that all of the terms individually, before we apply that alternating -1 value, that all of those terms, u sub 1, u sub 2, u sub 3, are positive. 2, we need to show that the u sub n's are eventually non-increasing. So they may have been increasing values, but at some point they level off and they stop increasing. So they're either remaining constant or they are decreasing. And we want to show that for a term following a preceding term, that term is either less than or equal to the one that came before it. So the term before is bigger than the following term, or equal to. And then we want to show that as the term becomes infinitely further out, as my index is infinitely large, that value becomes smaller. And if you look at the two examples we talked about in our last video, the two examples which were convergent, you notice that those fractions, that denominator became larger, the fraction became smaller and smaller and smaller as we traveled down our terms in the series. And the reason we can kind of show this, and I've pulled a picture in here, so we look at adding some positive term, which takes us over here, and then we may subtract a negative term, and then we add a smaller positive and subtract a smaller negative. And so as these terms are decreasing like this, what you start to notice is eventually they tend towards some value, some limit, something that the sum of the series ends up becoming equal to, or the limit of the series. All right, so hopefully this visual kind of helps you make sense why, if those terms are decreasing and they are alternating, we can say, well, it's converging to some specific value, in this case, L. So here we have an example. We're going to consider the series n equals 1 to infinity of -1 to the n plus 1 power times 1 over n. And this is one of the series I listed out at the beginning of our first video in this section. So we're talking about the harmonic series, which is generally divergent, but because I have this alternating term, this -1 raised to a power, which is what makes it alternate, we're going to be able to show that this alternating series is actually convergent. And so in order to apply our alternating series test, we can conclude convergence if we state that, all of these u sub n's, all of these 1 over n's are positive values. So part A of this, or my first part, I'm going to show what those terms would be. And if I started listing out my terms, I would get 1 over 1, 1 over 2, 1 over 3, etc. And we can see that as I list these out, all of these terms are clearly positive. So before the alternating part is applied, everything's positive. And then at some point we want to show, for part 2, that they are non-increasing. And we don't say decreasing because it could also remain constant, but non-increasing. And in this case, it's very easy for us to see that these values are getting smaller. So they are non-increasing. And the third step, showing that u sub n approaches 0, well, that's very easy. I mean, if we go and consider the millionth term in this series, 1 over 1 million, that's pretty close to 0. It's not 0, but it's close to 0, and close enough that we can say that the limit of these terms, as n becomes infinitely large, the term value approaches 0. So in this situation, we can say that this alternating series is convergent by the alternating series test. And I've pulled in a picture here that we are going to think about. So I've pulled in a picture here that kind of helps us think about what we're what we're looking at. So part A of this graphic, this is just showing the series or the sum of that regular harmonic series, 1 over n. And as we look at adding those values and summing, we start to notice it goes above some specified constant, right? So the index, as the index increases, eventually we become larger than some set constant, and there is no limiting factor. So this harmonic series is divergent. But when I put the alternating portion in there, you start to notice that we have values above and below. And if we start adding and subtracting these together, as I did on that last example, you'll notice that these pluses and minuses here, they begin to approach some limiting value. They converge, and in this case, they converge towards the natural log of 2, approximately 0.69.